Hey Wheaton North, Mr. Yergler here. This video is going to be a little bit deeper dive into lattice energy. Let's get started. Lattice energy is driven largely by Coulomb's law. And Coulomb's law really controls a lot of what's going on when we're talking about atoms because all we really have is charged particles. And so Coulomb's law, again, is the quantity of the charge is directly proportional to the force required, the force between them or the force required to remove them. And it's inversely proportional to the radius or the distance between them, right? So to increase the force between two particles, we can either increase the charge of those particles or we can decrease the radius, decrease the distance between them. And these two factors play a huge role in what's called lattice energy. The lattice energy, the official definition, is the energy released when ions in the gaseous state come together to form an ionic solid. Emphasis on the energies released, okay, when we're forming the crystal. So let's look at this example. Increasing the force between them is done by decreasing the radius between them. If you look at Kf, these are large ions, and so the centers of them are relatively far apart. The radius is relatively large. When you look at lithium fluoride, this is going to take greater energy to remove, so it's going to have a higher lattice energy because the particles are closer together because lithium is smaller than potassium. An example of this could be sodium chloride. And when you have the two ions and they come together to form the more stable solid crystal structure, that releases energy. I can't emphasize that enough. Notice that the energy change here is negative. Delta H is known as the enthalpy, and it's negative because this is an exothermic reaction. It's releasing energy because we're increasing the stability of the system. If you think about our charged particles as very separate, they're relatively high in energy, and when they come together, they actually decrease in energy. They release that energy. That the potential energy goes down because it's a more stable state down here than it is up here. Let's look at a couple examples. In this example, sodium fluoride and magnesium oxide, the distances between them are relatively similar. Magnesium is a slightly smaller ion, and so it's a little bit smaller radius. But these are going to have actually vastly different lattice energies because of the charges. These are only +1 and -1, while these are +2 and -2. And so this is going to take a lot more energy to remove. We could also look at copper sulfate. Now in this example, we have +2 and -2, but look at the size of the atoms. In this beryllium oxide, we also have +2 and -2. So the charges are the same, but beryllium oxide is going to require a much greater energy to remove all of these ions and separate them into the gaseous state infinitely far apart so that they're not attracted to each other anymore because they're much smaller particles. Copper sulfate is an ion that's made up of 5 atoms, and so it's a relatively clunky big molecule, or big ion I should say, and because of that size, that increases increases the size between the atoms, and therefore requires less energy to separate them because the radius is bigger. All right, that's really all we need to know. You need to understand the role that the quantity of the charge plays, and then the distance between the particles plays in just a qualitative sense. We're not going to actually be calculating any lattice energies, but we need to be able to identify this one is going to have a higher lattice energy than that one. All right, and that's all there is to it. This is Mr. Yergler signing off.